it comes out to be 35.3 degree. So another forms of Snell law can be derived from the definition of index of refraction. So n is c upon v, from which v is c upon n. So v1 upon v2, this is c upon n1 divided by c upon n2. Cancelling c, we get v1 upon v2 is n2 upon n1. So these are the two forms of Snell's law combined together here now. So theta 1 upon theta 2, it can be written as v1 upon v2, or it can be written as n2 upon n1. n1 and n2 are refractive indices, and v1 and v2 are velocities. Velocity in one medium, velocity in second medium. A simplified form of Snell's law. Since the indices of refraction for many common substances are usually available, Snell's law is often written in the following manner. So n1 sin theta 1, this is n2 sin theta 2, this is the simplified form of Snell's law. The product of index of refraction and the sign of angle is same as the in the refracted medium as for the incident medium. So n1 sin theta 1 is n2 sin theta 2. Another example, light travels through a block of glass, then re-emerges into air. So from air to glass and then again to air. Find angle of emergence for given information. So by this time I think you might be able to solve this problem orally. So in the previous slide we have seen in under such condition the angle of incidence and angle of emergence are same, because the light is traveling in air, after passing through glass it will come back again in air. So this angle will be same. So what we have to find is we have to find the angle of emergence for the given information. So information what is given to us, that this angle of incidence is 50 degree and refractive index of glass is 1.5. So using this Snell's law, that is NA sin theta A is NG sin theta G, we can find this sin theta G. So sin theta G, this will, substituting these values, this will come out to be 30.7 degree. So sin theta G comes out to be 30.7 degree. Finally, now what we have to find? We have to find this angle, that is angle of emergence. So theta G, this is angle of incidence for this glass air interface. So from geometry, note that theta G is same for next interface. So ye theta G is theta G, ye they are same. So here angle of incidence, this is now 30.7. So now again applies Snell's law to this second interface. So for second interface, applying Snell's law, theta, this emergence will come out to be 50 degree. So just see it is same as the angle of incidence. So angle of incidence and angle of emergence, they are same. So using Snell's law we have solved this problem. So Snell law, it will be applied to both the interfaces. First इस पे apply करेंगे इस interface पे, उसके बाद second time second interface पे. Now this is the third form of Snell's law. Snell's law now can be represented in terms of wavelengths also. So just see, the energy of light is determined by the frequency of the electromagnetic waves, which remains constant as light passes into and out of medium. So when light passes from one medium to another medium, its energy remains same. So energy remains same means frequency is same. There is no change in frequency because energy depends upon frequency. Also we know that velocity is frequency into wavelength. Velocity change होएगी तो wavelength change होगी. Frequency तो change हो नहीं रही because energy change नहीं हो रही. So this ratio of velocity in Snell's law, it can also be now represented as ratio of wavelengths. So just see here what is happening here. We know this velocity is frequency into wavelength. So velocity in air is frequency in air into wavelength in air. Similarly, velocity in glass is frequency into glass into wavelength in glass. So VA upon VG, this is F lambda A upon F lambda G, FF cancel हो गया. So that means VA upon VG can also be written as lambda A upon lambda G. So that means now this Snell's law, sin theta 1 upon sin theta 2, this is equal to v1 upon v2, and also this is equal to lambda 1 upon lambda 2. So lambda 1 is wavelength of light in first medium, and this is wavelength of light in second medium. So just see, wavelength is shown here. This is wavelength in air and this is wavelength in glass, and naturally the wavelength in air is greater than wavelength in glass. So now all the three forms of Snell's law are combined here in this slide, the many forms of Snell's law. Refraction is affected by the index of refraction, the velocity and the wavelength. So Snell's law, sin theta 1 upon sin theta 2 is n2 upon n1, is v1 upon v2 is lambda 1 upon lambda 2. Lambda 1, lambda 2 wavelengths, v1, v2 velocities, n2, n1 they are index of refraction or refractive index. So these are the three forms of Snell's law. So another example, a helium neon laser emits a beam of wavelength 632 nanometer in air. Okay, now wavelength is given. Now we have to use this another form of Snell's law of lambda 1 and lambda 2. So wavelength is given here. Refractive index of air, we know it is 1, it is also given. So what is the wavelength inside the slab of glass? So glass may know what will be the wavelength of the helium neon laser light. So given is refractive index of glass, refractive index of air, and also the wavelength of helium neon laser in air. We have to find its wavelength in glass. So using that Snell's law, lambda a upon lambda g, this is ng upon na. So na lambda a upon ng is lambda g. So these are ratios of refractive indices, and this is ratio of wavelengths. So in this formula, substituting all the values, we can find the wavelength of this helium neon laser in glass. So solving this, the value comes out to be 421 nanometer. So wavelength of helium neon laser in glass will be 421 nanometer. So note that the light, if seen inside the glass, if we see this helium neon laser inside the glass, it would be blue, but after coming outside in air, it will appear red, क्योंकि वापस आ गई है, तो it will appear red to the eye. But if we see inside the glass, then this will appear to be blue, because its wavelength is different inside the glass. Now next, another phenomena related to light is total internal reflection. अभी तक हम रिफ्लेक्शन और रिफ्रैक्शन की बात की है. Now this is another phenomena, total internal reflection. So we will try to solve few problems on this topic also. So when light passes at an angle from a medium of higher index to one of lower index, the emerging ray bends away from the normal. So this is your refraction only, but now the condition is that the incident ray is going from a denser medium toward a rarer medium. So when the angle reaches a certain maximum, it will be reflected internally. So see what is happening here. The condition is the light ray is moving from a denser to rarer medium. So as the angle of incidence increases, the angle of refraction also increases. So for particular value, the angle of this refraction becomes 90 degree. So this angle of incidence is called critical angle. Now if the angle of incidence becomes greater than the critical angle, the refracted ray come back into the same medium, and this phenomena is called total internal reflection. So the critical angle theta c is the limiting angle of the incident in a denser medium that results in an angle of refraction equal to 90 degree. So critical angle वो angle of incidence है जिसके लिए angle of refraction is 90 degree, and total internal refraction happens when theta angle of incidence is greater than theta c. So here it is shown, when angle of incidence is say 45, refraction is 70, for 48 81, for 49 this becomes 90. As soon as now the angle of incidence will become greater than this critical angle, the phenomena of total internal reflection will occur, means the light will come back into the same medium. So this is total internal reflection. So here the conditions are that this n2 is less than n1, theta c critical angle है, तो angle of incidence has to be greater than the critical angle, and the formula we have for critical angle is sin theta c is n2 upon n1. So sin theta c is n2 upon n1. So another example now based on this phenomena of total internal refraction. Find the critical angle of incidence from water to air. So for water to air we have to find the critical angle. So for critical angle we know this angle of refraction is 90 degree. So we know the angle of refraction, we know both the mediums. So we have to find the critical angle, value of critical angle. Refractive index of air is 1, refractive index of water is 1.33. So using this formula, Snell's law, NW into sin theta c is NA into sin theta A. We have to find the value of theta c. Theta A is 90 degree. We know its value, we know refractive index of air and refractive index of water. So substituting all these values, the sin theta c, this comes out to be 48.8 degree. So the critical angle for this situation comes out to be 48.8 degree. So for the we know the condition, the requirement for this total internal refraction is that n1 is greater than n2. So we can also write a short form of this formula, that sin theta c is n1 upon n2, because we know sin 90 is always 1. Sin 90 value 1 है, तो instead of writing sin theta c upon sin theta a, so we know sin theta a is 1, so we write sin theta c is n1 upon n2. So now another phenomena is that of dispersion. So dispersion is the result of refraction only. So what happens? Light when enters into a prism, so the 7 colors of light are there, they have different wavelengths, so they suffer different refraction. As we have seen in previous slide that this refraction depends upon the wavelengths also. So short wavelengths are bent more than long wavelengths. Light is bent and the resultant color separates. Red is least refracted, violet most refracted. So dispersion is the result of refraction only. In dispersion the light splits into its 7 different colors. So this dispersion by prism is shown here. Dispersion is the separation of white light into its various spectral components. The colors are refracted at different angles due to the different indices of refraction. So when white light passes through a glass prism, blue is bent more and red is bent least. सबसे ज़्यादा रिफ्रैक्शन ब्लू कलर का होता है, रेड का सबसे कम होता है. So a rainbow is shown here, example of rainbow is given. So the variation in refractive index with color is called dispersion. A rainbow is an example of dispersion in nature. Tiny raindrops act as prisms separating the colors in white light rays from the sun. So now this is Lenz's formula. Lenz's formula, what is Lenz's formula? This is relation between u, v and f. So the Lenz's formula for spherical lenses is a relationship between the object distance u, image distance v and the focal length f. So magnification का formula, magnification produced by spherical lenses, this is given as height of image divided by height of object, or size of image divided by size of object. And another way to represent magnification is v upon u. So v upon u, magnification is v upon u, or this is h1, hi upon ho, that is incident, image and object, size of image, size of object, and this is your Lenz's formula. 1 upon v minus 1 upon u is 1 upon f. So power ka formula is, power is given as 1 upon f, f is reciprocal, f is focal length of the lens. So power is given as reciprocal of focal length, or focal length can be given as 1 upon p. SI unit of power is diopter, power को diopter में measure किया जाता है. 1 diopter is the power of a lens whose focal length is 1 meter. The power of a convex lens is positive and the power of a concave lens is negative. So with this I conclude my lecture. Hope all of you enjoyed. Thank you.